Hello guys, it's Anas Alaa, a freelancing Houdini visual effects artist. This is a free section from the course The Ultimate Houdini Dops on CGCircuit. This free section is going to talk about curve forces in Houdini. We are going to create curve forces from scratch to control our smoke or particle simulations. The forces are going to change our simulations to make our particles or smoke go around or towards or along a curve that we draw. So this lesson isn't just about creating the forces. We are going to create controls for these forces and a final digital asset that can be used for any smoke or particle simulations. This section has multiple parts and I hope you enjoy it.
Hello guys, welcome in this video. In this video we are going to start a new example of creating custom forces in Houdini to derive the simulations. By custom forces we mean a field or a custom velocity field that drives the simulation, as we did with the Maelstrom or the ocean vortex example. So what the curve force does is that it pushes the simulation, for example, the smoke simulation, along a curve. So what we do is that we create a curve, for example, okay, and what we are going to do is that we are going to create three forces that deal with this curve. We are going to create a force that pushes the smoke along the curve, so our smoke follows our curve, and we are going to create another force that makes our smoke push towards the curve, because we need our smoke to be adhered to our curve, okay? And another force that makes our smoke twist around our curve here. So it's going to twist like this. And surely we are going to create controls for these three forces, okay? So we are going to create a suction force that is going to push the simulation towards our curve, and a follow force to make the smoke move along the curve, and the orbit or twisting force to make the smoke twist around our curve. Actually, in Houdini, there is a node called the gas curve force, and it does roughly the same thing here, but I don't like it, okay, because I don't have the results that I want, okay. And of course, guys, it's better to create nodes and know how they work as we did before. It's going to open your eyes and broaden your mind in Houdini and makes you able to create more custom things that fit your situation. So this gas curve force is available, and we are going to create our example. And actually our example is going to be there is going to be differences between our example or our created curve force, or the version that we are going to create, and there will be differences between the version that we are going to create and the gas curve force. Surely we are not going to create the same thing. We are going to make it with some difference. So now what we are going to do is that we are going to create a curve first. Just draw a curve, and then we are going to resample this curve. We're going to create points along this curve, okay, and we are going to use a node called polyframe to generate tangential vector along this curve. So this polyframe node generates, I'm going to choose a different color. It generates a tangential vector along the curve. So the tangential vectors are going to look like this from upwards, downwards along our curve. And we are going to set these vectors as the normals. Okay, so these are going to be our normals. We are going to create normals that are tangential to our curve like this. And what we are going to do next is that we are going to create a volume, okay, with the same bounds of this curve. So we are going to have the bounds or the boundaries of the curve like this, and going to make a volume with these boundaries. Okay, surely a volume is full of voxels or is composed of voxels, as we said before. Then we are going to do all the magic inside a volume VOP node. And the volume VOP node, I think this is the first time we are using it. It's like the same, it's like it's just the same as any VOP, okay, but it deals with volumes. It's more like the gas field VOP, where we dealt with the volumes or fields. We accessed our different fields and did a lot of things with them. So we are going just to create this volume VOP, okay? And this volume VOP has 4 inputs. We are going to connect our volume to the first input, and we are going to connect our curve points to the second input, okay? So now we can deal with our volume that we are going to call our velocity volume or the velocity field. Okay, then what we are going to do inside this volume VOP is that we are going to use something called point clouds. And this surely needs more explanation because this is the first time we use the point clouds, and they are very, very useful, and we are going to use them a lot. So what a point cloud does, the point cloud is a node called point cloud open, and this node just takes the position, okay, and take another geometry that you want to search into. So for example, you can give it the position of some points, okay, if you have just the points of, for example, particles just flowing into just a simulation of particles like this. And for example, these particles are going to reach an object, and this object surely has points or is composed of points. So if you connect the points or the particles to the first input, or sorry, if you connect the particles or the particle position into this position of the point cloud open, and connect your geometry here to the geometry input, what you are going to do is that you are going to search around these points in a specific radius. So if you set the radius, for example, to 1, the point cloud open is going to search for something around this point with the radius of 1 meter. So here you have the radius of 1 meter. You can set it to, for example, 3. It's going to be a bigger circle like this. So it's just searching around the points that you give the position of, and you are searching into this geometry that you are inputting here. So, for example, if the point here, if this particle here, let me select this particle, if we are searching here in a radius like this, for example, and this radius finds this point here of this geometry, or it may find 3 or 4 or 10 points. You can set the maximum number of points that it finds. Okay, now after you found these points, you can grab things from them, or you can manipulate them in a lot of ways. So there are a lot of point cloud nodes, but we are going to use a node called PC filter. And this node grabs the specific, just grabs specific attributes from the found points. So if it finds, for example, 1 point, and we want, for example, the normals or the color, for example, from this point, or any other attribute, it is going to grab it. Okay, but if it finds, for example, 3 points, and the 3 points have different values of normals, for example, it's going to grab the average of the points. So it's going to grab the average normal or the average color or whatever you choose. So this is what a point cloud does. Surely we have a lot of point cloud nodes, okay, but this is the node that we are going to use, and we are going to use another node called point cloud num found. This node just returns the number of points that this point cloud open finds. Okay, so we are going to use it. So let's return to our volume VOP. What we are going to do in this curve force example is that we are going to input the position of the voxels of our volume into this point cloud. Okay, so we have the position of these voxels, and we are going to input our curve as the geometry. So our curve is going to be our geometry that we are searching into. And we are going surely to choose a search radius, for example, of 1. So we here have our voxels. We're going to use the same color, our voxels, and we are going to do a search radius. We are going to use the point cloud to find the normals of the curve within a search radius. So for example, we are going to use a search radius of 1. So in the voxels that are located 1 meter from this curve, for example, if a voxel is here and the distance between it and the curve is within 1 meter, so it's 1 meter or less, okay, to the curve, it's going to find specific points near it from the curve, and we are going to grab our normals of these points. So now we have our voxels that are near to the curve depending on the search radius, and we grabbed the normals of the curve which are tangential to these voxels. So we have now our normals. Okay, now what we are going to do is that we are going to negate these normals. So these normals are just tangential to our curve, but they are upside down. We are going to negate or just have the opposite direction of these normals. So the opposite direction is just downwards, upwards, and they are going to be tangential to our curve. Okay, so now we have vectors that follow. We have vectors that follow our curve. So in the voxels here near to our curve, let me draw it here. In the voxels here near our curve, we are going to, let me draw it here. If we draw our curve here, bigger version of it, in the voxels near our curve, or covering our curve within a search radius of 1 meter, for example, we will have vectors that are following our curve. So voila, here you have now your follow force. So this is the first thing that we are going to do. We are going to use the point clouds to search for the normals, and we're going to negate them to have our follow force. And this is our first force. Now, after we already edited or modified our velocity volume inside our volume valve to have the follow force, okay, we are also going to do something to generate our suction force vectors. With the point clouds, we can grab the position of the points on the curve. Okay, so for example, if we have a voxel here, okay, and the point cloud finds this point, okay, and you grab the position of this point that you found. The position is an attribute that you can grab with the point cloud filter node. If you now subtract the position of this point, that you found by the point cloud minus the position of your voxel, what you are going to have is a vector coming from this voxel to this point. And we did the subtraction process a lot. So if you do this with all the voxels within the search radius of 1, for example, you are going to have in these voxels vectors that look from the voxels towards your curve. And surely these vectors are going to represent our suction force that is going to attract our smoke, for example, to our curve. This is our suction force. So now we have two forces. The third thing that we are going to do is that we are going to take these vectors that look towards our curve, okay? So we are going to take the subtraction process here, or the vectors that are that resulted from the subtraction process, and we are going to do a cross product between them and our normals, okay? And our normals that are tangential, okay? So our tangential normal normals. So to be able to draw this, let me just extend my curve here. If we take the cross product between a vector looking like this and a vector like this towards our curve, the resulting vector perpendicular to them is going to be a vector that is tangential to both of them, like, and of course I can't, draw this in 2D here, but if you have your curve and, for example, you take the direction, this tangential vector here, and you do a cross product between it and the vector that makes our makes or sucks the vector that attracts your simulation to the curve, the resulting vector is going to be perpendicular to both of them. So this vector, okay, if you see here, is just a vector that is going to push your simulation in this way. So it's going to generate vectors that are going to be twisted around our simulation. Of course, it's very hard to draw it here in 2D, but the result is going to be very, very clear and apparent in Houdini. So now you have your twisting force. Okay. This is the general idea that we are going to do in our simulation. We are going to generate our three forces. We are going to add them together and export them as our velocity volume.
Hello guys, it's Anas Alaa, a freelancing Houdini visual effects artist. This is a free section from the course The Ultimate Houdini Dops on CGCircuit. This free section is going to talk about curve forces in Houdini. We are going to create curve forces from scratch to control our smoke or particle simulations. The forces are going to change our simulations to make our particles or smoke go around or towards or along a curve that we draw. So this lesson isn't just about creating the forces. We are going to create controls for these forces and a final digital asset that can be used for any smoke or particle simulation. This section has multiple parts and I hope you enjoy it.
Hello guys, this is what we are going to have as a result. This is a simple smoke simulation and we are sourcing the smoke from a sphere, and as you can see our force follows the curve and the smoke also twists around our curve. If you see here from this angle, for example, it twists around here. So if you see here, it is twisting and following, and it's attracted to our curve. And we are going to add a lot of controls here to the simulation, and we are going to create a force like this or a field like this. So this is just a simple smoke simulation, and we created this example before, and we have our curve object here. This is just a curve node, and we drew this curve here, okay? And we are going to create this from scratch. Surely we are going to use the velocity update input here because we are affecting our velocity field. So we are firstly going to create a SOP guide node, and this node here is just a SOP network, okay? But this SOP network is not going to be executed, okay, or calculated in our simulation unless you press on show guide geometry or when you call anything that happens inside it. Okay, so this node here just has the option of show guide geometry. Okay, and this option here is here, and this option is very great. We can show the thing that inside our SOP, okay, without calculating it every time, and it's calculated also when you call the nodes that inside it, and this is going to be more clear when we deal with it. Okay, so if we enter here, here we are in a SOP network, so you have all of the nodes that you can use in the SOP. For example, you have the poly, extrude, you have all of the nodes that you are using in SOP networks. And this is great in Houdini. You can use SOPs inside DOPs. You can use any context inside any context. Okay? So the first thing that we are going to do, we are going to have an object merge. Okay? And in this object merge, we are going to reference our curve. So now we are getting our curve from the SOPs. Okay. Then after we do this, we are going to resample our curve. So now we are adding points to our curve every length here. So every 0.1 of length, we are going to add a point. So if we show our points, they are here. Okay, I don't know why they are small, very small like this, but here we have our points. And we can make the length less, and it's going to add more points. Okay, but we are going to stick to 0.1 now. So now we have our curve resampled. What we are going to do after this, we are going to create an attribute wrangle. Okay, and this attribute wrangle, we are going to use it to create an attribute called length scale, and I'm going to tell you what this attribute does because this needs more clarification. So if we create another scene here, okay, if we have our curve like this, for example, let's draw a picture curve like this, for example, and we have points along the curve. By default, the points are ordered along the curve. So this is 0.1, this is 0.2, 3, 4, 5, 6, 7. Okay, so now we have 7 points, but actually the numbering starts in Houdini from 0. So the first point will have the number 0. Okay, because this is going to have to be this is going to have significance. Okay, so we have in Houdini an attribute called pt num, which represents the number of the point. okay, 0, 1, 2, 3, and blah blah blah. And we have another attribute called numpt, which represents the whole number of points. So we here have 7 points, okay? So to create a length scale attribute that represents the length or the distance between this point and the end of the curve. So for example, here we may have a length between this point here, or a distance between this point number 1 and the end of the curve here. We can have a distance of 0.5, but here in this point number 2, the whole length is bigger to the end of the curve. You have all of this length, so here it may be 1, and here we have this length towards the end of the curve. It may be 2 or anything, okay? So this is going to be our length scale. To do this, we can just divide our point number over the number of points minus 1, okay? So let's take this intuitively. Okay, for the point number 1, for example, we will have a length scale of 1 over, we have here 8 points from 0 to 7, we have 8 points, so sorry, 8 minus 1 is going to be 7, and for the point number 2, it's going to be 2 over 7, for the point number 3, 3 over 7, 4 over 7, okay, 5 over 7, 6 over 7. Then in the last point, it's going to be 7 over 7, and it's going to be 1. And for the point number 0, it's going to be 0 over 7, which is going to be 0. So if you now notice here, we are having now an attribute that comes from 0 and increasing here to 1 over 7, 2 over 7, 3 over 7 until we reach 1. So now we have an attribute from 0 to 1, which represents intuitively the length from the point to the end of the curve. Of course, these numbers are not the actual length, but they are numbers increasing from 0 to 1, and they increase more from 0 to 1 depending on how far the point is from the end of the curve. So the last point will have a length scale of 1, and the first point is going to have a length scale of 0, and we're going to increase from 0 to 1, okay, until we reach the end of the curve. And this attribute is going to be very, very useful. We can manipulate our forces depending on how far this point here is going to be from the how far the point is from the end of the curve, okay? So we can manipulate our force along the curve from the first, or from the end, from one end of the curve to the last point at the other end by this length scale. Okay, we can, for example, choose the points at the end of the curve to have larger force or a bigger amount of force, and the points at the beginning, for example, we can choose to make the force smaller at these points. So this is going to be great. And we are going to do this inside of, I'm sorry, we're here having the sub guide here. We can define our length scale attribute, and this is going to be our point number divided by the number of points minus 1, okay? And because the point number and the number of points are integer attributes and our length scale is a float, so the integer attributes is just a number without fractions, and our length scale is a float, so it will have fractions. So we need to convert the integer attributes into float by the float function. Okay, the float here, we can type just float like this. And if we now see here, I don't know why it's not working. Sorry, the number of points shouldn't have S here. It's going to be like this. So you have now your length scale. You here have the point 0. It's just 0 length scale. And the point here, the last point here, will have a length scale of 1. And you have increasing values from 0 to 1. So this is really great. You have now your length scale. So now after we do this, we want to create our tangential vectors. So to do this, we should create a node called polyframe. Okay. And this node, if we visualize the normals now, it computes the normals to be like this, because we are choosing the normal name here and putting the n, which is the normal. But we can disable this, and we here have the tangent name, which represents the tangential vector. We can here, instead of tangent to, if you middle click, you'll add this tangent to. We want to store the tangential vectors into our normals because they are more easier to access. Okay, so if we do this, if we put the normals, we here have our normals tangential to our curve here, like this. Okay, if you see here, yeah, they are tangential from upwards downwards. Okay, now we want to create the volume that bounds our simulation. So we are going to create a bound node. Okay, this node takes your geometry and generates a bounding box that bounds this geometry. So here we have a bounding box here bounding our curve, and now we want to create our volume, so we can create a volume node, and this volume node here create a volume. So if we choose here vector volume and call it, for example, velocity, okay, we middle click now, it creates a Houdini native volume. Here a vector vel.x, vel.y, vel.z. It's just a vector volume. Okay, and maybe we can give it a value, any value. So you'll see your volume here in the viewport, but we don't want this. We want it to be 0. And you can connect your bound node to this volume. So here we can now see our volume. If we see here our bounding box and our volume, I think there is a problem maybe in my viewport or something. Set an initial value of 1, for example. Yeah, it's creating our volume here. Okay, but I don't know why it's not visualizing in our viewport when it's 0. Anyway, we can now in the uniform sampling here, which defines the resolution of our volume, we can set it to by size, and this is the division size. Okay, now we are creating our velocity volume, and it's empty now. After we do this, we can create our volume VOP node, and we are going to connect our volume to this volume VOP node. And if you enter here, this volume VOP is just like the gas field VOP. You can manipulate your volumes. You can bind them by a bind node, and this is the great thing inside this node. Now we will connect our curve to the second input of our volume VOP, and this is because we want to use the voxels as a position of the point cloud, and we want to search within a search radius in the curve points or the curve geometry, like we said before. So here in the volume VOP, we can disconnect this. We have here the position of the voxel, okay, and we can access our fields or volumes with bind nodes like we did in the gas field VOP. Okay, so now we are going to create our point cloud. So if you type point cloud, you'll have a bunch of nodes here, a bunch of point cloud nodes. We have here the point cloud open, the point cloud filter, and the point cloud num found. These nodes that we are going to use now. So let me firstly add my PC open or the point cloud open. And here in this point cloud open, you have the position, which we will connect here, the position of the voxels, and you have the file here or the point cloud texture here, which refers to the geometry that we want to search into. So if we connect this now to the op input 2, which is this here, which is our curve, we can now search through our curve, and we here have the search radius, okay, and we have the number of points that we are going to grab within the search radius, and surely we are going to average the attribute that comes from these points if we use the PC filter node. So what I'm going to do now, I'm going to promote the radius here, because this is going to be the radius of search that the user can control, and we are going to rename it to max radius, maximum radius, and the default I'm going to set it to 1. Okay, now we have our maximum radius. After that, I'm going to add my PC filter node. Okay. In this PC filter node here, you can grab an attribute here. You can type the attribute in the channel, okay, and select the signature of the attribute. Is it a float, an integer, a vector, and anything? So we now are going to grab our length scale of the curve. If you remember, the length scale was an attribute from 0 to 1, depending on how far the point from the end of the curve. So we are going to grab this length scale. And what we are going to do now, we are going to control our radius based on this length scale. So we can give the user the ability to control the radius of, or the search radius of the point clouds based on this length scale. As we did before, we created ramps before. Let's rename this first to DC filter length scale. If we add now a ramp parameter
And I think you are familiar now with the ramps. We're going to call it spline ramp, and we can pull it along length radius ramp. And we can rename it here, radius along curve length, for example. Okay, and this point here is going to represent the end of the curve. Okay, where the length scale is 0, and this point is going to represent the other end where the length scale is going to be 1. And now we can multiply this here. We can multiply our radius, okay, by this length scale. So now we are just manipulating our radius as we did a lot before by ramps in the masking videos. We are manipulating our radius, okay, along the length of the curve. And this is the usefulness of our length scale. So now we have our ramp here controlling our radius. So I'm going to make our ramp one like this, okay, because I don't want our ramp to change anything in my simulation. For now, if the user wants to change the radius, but I want a uniform radius. Okay, so now we have this multiply. We can create a null just here. And this is going to be our local radius. Okay, this is our local radius here. Now we can use this manipulated local radius here to open a new point cloud. Okay, so now instead of using this radius here, we are going to use the radius that we already edited by the length scale attribute to search for the points in the curve. So we are going to connect the same things that we connected in this first point cloud, but now we are using a different radius that the user can control by the length scale. And now we can filter two attributes. We can filter the position of the points of the curve. And if you remember, we are going to use this position to create our suction force and our cross product that is going to generate our twisting force. Okay, and we are going also to use another PC filter to filter our normals. Okay, so now what we are going to do, we are going to create our forces in the way that we already discussed. Let's firstly create our along force. As we said, the normals are the tangential vectors, but we want to negate them to get the right direction. And this is going to be our along force. We are going to normalize it because we want a length of 1, okay? Then
we are going now to create our twisting force, or firstly, let's create our suction force. As we said, we are going to subtract the position of the points of the curve minus the position of the voxels, and this is going to give me a vector from the voxels to our curve, and we already discussed this, so this is going to be my suction force. We are going to normalize it. Okay. Then lastly, we are going, want to get rid of this. We are going to create our twisting force using a cross product node. Okay. Use a cross product node here and do a cross product between the normals and our subtracted vector here, and we already discussed this. This is going to be my twisting force. So now we have three forces. We have our along force, we have our twisting force, we have our suction force. We can add the three forces together. Okay, then we are going to add a bind export now to export these as our velocity volume that we already created. So now you'll start having something here in the viewport. If we go outside now, we can visualize this volume using a volume trail, as we already did before, I think. So to do this, we are going to use a node called volume slice, and this is going to give me a slice here along my volume, and we can use a volume trail node. We can connect this to the points to trail, and here the velocity volumes. And here we can, in the velocity volumes, we can choose our vel.x here. Let me unshow the points and the normals. So if you see now, we are having something here. Okay. So I don't want to calculate the force in the whole volume. I just want to calculate the forces in the voxels that found already points from the curve in this point cloud. Okay, so if this point cloud found points of the curve, then we are going to calculate all of these forces. Otherwise, we don't want all of these forces to be calculated in the other voxel. So we are just going to calculate of the forces in the voxels within the search radius. So to do this, we are going to use the other node that is called point cloud num_found. So this node returns the number of points that are found by the point cloud, and if there is no points found in the voxels that are beyond our search radius, it's going to return -1. So we can now compare the number of the points. So if it finds points, the number is going to be greater than 0. So if we find points, okay, or the number of found points are greater than 0, we are going now to create an if block like we did a lot of times. So This is our if block. We can now output our force here if the condition is true, but if the condition is false, we can now create bind node. Okay, and bind our velocity vector. I think Houdini.
Hello guys, it's Anas Alaa, a freelancing Houdini visual effects artist. This is a free section from the course The Ultimate Houdini Dops on CGCircuit. This free section is going to talk about curve forces in Houdini. We are going to create curve forces from scratch to control our smoke or particle simulations. The forces are going to change our simulations to make our particles or smoke go around or towards or along a curve that we draw. So this lesson isn't just about creating the forces. We are going to create controls for these forces and a final digital asset that can be used for any smoke or particle simulations. This section has multiple parts and I hope you enjoy it.
Our condition is going to be if there are points. So this is going to be my condition. And if you see now, we have our forces calculated only in the points, in the voxels within the search radius. Okay. And here we have our forces. So we can add a multiply node after each force. To just have a scale parameter or a multiplier parameter that, and this is a thing that we already did before. So this is going to be our follow force scale, follow force scale, and the default is going to be 1. Okay, we can also add a multiply here, multiply our twisting force here, or the orbit force. We can call it orbit force, orbit force scale, orbit force scale, and the default is 1. Then we can another multiply for our suction force. So this is going to be my suction force scale, my suction force scale. Okay. Now if we go outside here and set these forces to 2.5, 2.5, 2.5. Okay. I think there is a problem here. Oh, guys, I'm sorry. Here in the point cloud, I here want to filter the normals. I forgot to do this. And in this bound node, I think our volume is slightly smaller than we want, so I can increase the padding to make it bigger. Okay. If we now visualize it, oh yeah, this is great now. We can visualize every force alone. So if we just visualize our orbit force by making the other forces 0, as you can see now, we have the vectors around our curve. If we visualize our suction force alone, as you can see, vectors looking towards our curve. If we visualize our follow force, you'll have force following your curve like this, and we can add them together like this. So now we can add a null here, call it out velocity, and if we go now outside and visualize our SOP guide, it will not show what's inside here in the volume trail unless we show the guide geometry and play one frame. I think it's not being visualized because it will always visualize the output node if we delete it. Okay, maybe we can connect it to a velocity update, I think, maybe. Let me hide other objects. Why isn't it showing on the viewport? Yeah, here we go. Now it's showing when we press this show guide geometry. My viewport is lagging or something, so it's very buggy. I can visualize it like this. Okay, so this guide geometry is great now. Now inside here, we want to add some controls to our force for the user. Now what we can do, this subtract node here, we have now a vector from the voxel to our curve. What if we want to use this vector, okay, and add it as a control to be able to control our force when it is very near to the curve or far from the curve within the search radius. So for example, we can take the length of these vectors that come from the voxels to the curve and add a fit range, and we can fit them between 0 and 1. Then we can add a ramp, and this will control the force from just in the area of the radius around the curve. So for example, you can make your force less when they are far from the curve. You can make them higher when they are very near to the curve. Okay, so to do this, we can add a length node, and I think you are familiar with this now because we did it in the Millstorm or the vortex force. And we can add fit range. We want to fit this between 0 and 1 in the destination, but in source min and max, the source max, we just want to use our maximum radius. So when the force are are in the maximum, in the area of the maximum radius in this area or more, they are going to have a value of 1. When they are very near to the curve, or when the distance is 0, they are going to have a value of 0. And between, in these areas, you'll have ascending values from 0 here to 1 here at the periphery in the maximum radius area. And now we can add a ramp for each of these forces. We have already a multiply node here, so we can add a ramp parameter for each of these forces. So for example, we can call this suction force from curve ramp, and I like to use the informative names even if they are too long, because this will help you a lot during creating OTLs, because when you create a lot of parameters you may get lost. And for now I want my RAM to be like this, and we can multiply it here, of course, from the outside our RAM. I don't know why I just edit the default here. It doesn't edit it from outside. But anyway, we can also add another RAM for my twisting or orbit force. Houdini hangs a lot when I'm just recording. Suction force RAM or from curve RAM. I'm sorry, not suction, orbit. And orbit force from curve RAM. Okay, and it's a spline. Make it like this. Okay. And another ramp. I know that these operations or these steps are a little bit boring, but they are very important. Follow force from curve ramp. Then add it here. So now you have a ramp for each force where you can just make your force or control your force. So for example, you here have distance of 0, and here you have a distance of the maximum radius. You can control your force. Maybe here, if you can see now, we are making our suction force 0 when it's very near to my curve. We can do something like this, for example. If you see now, they are 0 and they are stronger here in this area. Okay, so this is the idea. And we can also control our global force, or the force after the addition of the 3 forces. So you can control your force as a whole by this multiply node. You can create a parameter, call it global scale. So now you can increase or scale your force as a whole. from outside. Maybe you can add another ramp parameter based on the distance for the whole force. Okay, so now this is going to control the whole three forces together, and you can call it global force from curve ramp. Global force from curve ramp, and we can add it here. Okay, there we go. We can also control each of these forces by the length scale. If we just create another point cloud filter to filter my length scale from this point cloud here, float length scale. So now we here are filtering my length scale. We can add a ramp now for each of these forces depending on the length scale, but I will leave this for you guys. I will just add my ramp here to control just the general force or the global force, but you can surely control your suction or follow or orbit force by three different ramps, like we did by from the distance, like we did in the distance here, like we did with the distance here. Okay, so here we can call this along or global force along length ramp, global force along length ramp. Okay, and it's a spline ramp on the outside. Let me make it like this because I don't want now my force to be changed by this ramp. And I connect it here. I connect it here. Okay. Okay. Here we go. We can here, if you can see, can make our force 0, for example, till the end of my curve. Okay, we can control along the length now. Oh, I'm sorry, I'm playing with the wrong ramp here. Sorry. Here. Where is it? Can see if you can see now. We can cut our force along the length of if we want. Okay, so this is a great control. I think now we have great controls. We can just now use this velocity field. You can guys just manipulate it as you want, but we can use this velocity field now in our simulation, and I'm going to show you how to do this. Now let's add this velocity field to the velocity of the simulation, because here it's just calculated in this sub network. We need to grab it from there, and as we said before, the sub guide is not going to be computed unless you show the guide geometry or you call the fields from it or the things from it. In this case, it's the velocity field. We are going to call it through a gas field VOP. Okay, so here we have our velocity. Here we need to call it there. And we will also want to add a null here for the curve, because we will need this reference, or we'll need the curve points. Okay, so here inside this gas field VOP, we here have two velocity fields that we want to grab, and we will mix between them in a great way. We're not going to add just this velocity field to the velocity of the simulation. I mean the velocity field here from the subguide, we will not add it directly to the velocity field of the simulation, but instead we are going to mix between them. So to access the velocity field, so we want to access the two velocity fields. The first one, if we create a bind node, okay, we can access the velocity field of the simulation. And if you play your simulation, if you play your simulation, this is the velocity of the simulation now. The smoke that is rising up like this, okay? And and if we want to grab the velocity field from the subguide, we can use a volume sample vector. I don't know if I used this before or not, but the volume sample, as we said, I think before, it samples the value of the voxels of a volume depending on this volume sample vector here samples the values of the voxels of a field or a volume, okay, and you connect it to a position, okay, and it sees the points or the voxels, or here in this case, so this volume sample vector here is going to sample our velocity values, okay. We just give it the position of our voxels of the simulation, and it sees, okay, the position of these voxels, it sees the position of these voxels in our simulation, and it says, hey, I'm going to sample the values of the velocity field that is created in the subguide in the voxels that near to the voxels of the simulation itself. So for example, to make this clear, here we have our density field, okay, and we have it's just a field composed of voxels. So for example, in this voxel, it has a position, okay, and this volume sample takes this position of this voxel, for example, and searches for the near voxels of, or the most near voxel of the velocity field of this subguide, and samples or takes the value of this voxel. So for example, it will sample the nearest voxel of this field here, which is this voxel, okay. So this voxel will sample the value here from the voxel that is that is nearest to it, okay. So to do this now, or to make this volume sample vector axis our velocity field that is in the sub-guide, we can't connect it here to the inputs. So to access our velocity field from the sub-guide here, we can, here in the inputs, we can either here select the input, first input or second input. We are going here to select the first input, or we can connect it to the first input here. Okay, and here come in this gas field VOP and inputs here, you have this input who can add a SOP path, and you can go to the SOP guide and sample your velocity field, which is really great. So now you are sampling your velocity field, and the velocity field of the simulation, you have the two velocity fields. What we want now is that we want to subtract these two fields. So now you have the difference between the two fields. We want, if the difference between these two forces is larger than or equal to 4, for example, we want this velocity field from the sub-guide to affect our simulation stronger, or to be the dominant in our simulation. But if the difference is less than, or if it's between 0 and 4, we want the velocity field of the simulation to be the dominant. And what will this do is that, for example, if the difference is 0, if the volume sample is mostly the same as the velocity of the simulation in a specific voxel, we don't want to add more of it. We just want to add some of the natural velocity that comes in the simulation due to the buoyancy and the smoke surely has temperature and it's floating. Okay, because we want our simulation to be natural. We don't want the smoke to stick very much to our curve. Okay, so now we have this difference. If we create a fit range here, I'm sorry. Firstly, we want to take the length here of the subtracted vector, and if we use fit range now, we here have the source min and max. If we set this to 4, now if the values, or if the difference between the velocity of our sub-guide is, and if the difference between the velocity of the sub-guide and our simulation velocity is 0, we are going to have a destination minimum of 0. And if the difference is 4 or more, we are going to have a destination of 1. And if the values, or if the difference is between 0 and 4, we will have ascending values from 0 to 1. Now, after we add this mix node, we can connect this fit range to the bias here. So this bias is from 0 to 1. I think we used the mix node before. If it's 0, it's going to use this input. If it's 1, it's going to use this input. Okay, so we want when the length here, or when the difference here is big, or is bigger than 4, okay, we want to stick with the velocity of this velocity field from the sub-guide. But if the difference is too little, or if it's 0, for example, we want to use the velocity of the simulation to add more natural effects. So now the simulation will go, and the difference in the first frames will be high because the smoke is going to float due to the buoyancy, so the difference is going to be larger than 4. So it's going here to use, or the velocity from the soft guide is going to be dominant, so the smoke will start now adhering to the curve and will follow the curve. Okay, and if the difference after the smoke adheres too much to our volume sample from the soft guide, then the velocity field from the simulation is going to be the dominant, because this will make our smoke, float more naturally by the temperature and the buoyancy. And this is going to be a balance here, and surely you can promote this source max parameter, and this can be controlled by the user. Okay, and what we can do now, we can bind export this as the velocity of our simulation. Okay, I hope this idea is clear to you now. If we now play our simulation, you'll find something like this.
Hello guys, it's Anas Alaa, a freelancing Houdini visual effects artist. This is a free section from the course, The Ultimate Houdini Dops on CGCircuit. This free section is going to talk about curve forces in Houdini. We are going to create curve forces from scratch to control our smoke or particle simulations. The forces are going to change our simulations to make our particles or smoke go around or towards or along a curve that we draw. So this lesson isn't just about creating the forces. We are going to create controls for these forces and a final digital asset that can be used for any smoke or particle simulations. This section has multiple parts, and I hope you enjoy it.
So this is what happens now, guys, when we played the simulation, and as you can see, it's not working fine. So here in the signature, we can set it to primitive name and type velocity. And if we play now, you'll see our smoke is following our curve now, which is really great. Now we can just increase the resolution of our simulation to something like this. And yeah, our smoke is now working, which is really great. Maybe in our sphere here, we have this division size, we can set it to something like this. And now if we press play, our smoke is working, which is really great. We can promote this parameter here, guys, the 4. Think we can call it max distance of mix, maximum distance of velocity blend, maybe velocity blend. Okay,
yeah, I think this name is a little bit intuitive. You can choose the name you want. Now guys, we can here in the gas field VOP set this input to grab our curve from our sub guide, and here we are going to open point cloud. Now we are going to select the position of the voxels and our curve points. Now we have our curve points. We can set the search radius to 0.5, and now we are grabbing the points from the curve. Okay, maybe we can go here in the sub guide and copy this maximum radius and paste relative reference here so they match with each other, and we can grab the position of the points of our curve. So now we are just doing the same thing that we did in the SOPs. We are grabbing the position of the curve points that are near to our voxels. Okay, and we can do a subtract between the position of the voxel and position of our curve point, and this is the same idea. We have now the distance between the curve points and the position of our voxels, so it's just the same idea that we did here okay, and we can take the length of this. Now we can control our velocity blend depending on the on how far the density field here or our simulation smoke from the curve points. The same idea. What we can do, we can just create a fit range node. Okay, and in this fit range we can, here in the source max, we can paste our maximum radius. Okay, so we are now controlling the simulation around the curve within the maximum radius here, and we can now set it from 0 to 1, for example, like this, and we can add another mix node, and we can connect this. Okay, so now we can control the smoke based on the distance between it and the curve. So if it has a distance between it and the curve of 1 or more, okay, we want this far smoke to follow the velocity of the simulation. We want it to be affected by the temperature and the buoyancy. This will make it more natural as it's going to float, you know, and it will not adhere to our curve. And this is going to be great because this smoke here will be naturally floating. It's just a smoke. We don't want it to be very, very sticky to our curve, and we want the far smoke to float upwards. Okay, and if it's not far or it's near to the curve, we want to use this velocity, and we can now connect this to our velocity. And if we now play our simulation,
So now here is our simulation. What we can do now, we can just here inside, we can scale our orbit force. We want it more, okay? And we need to add some noise to this simulation. To do this, we can add a gas turbulence node, the basic node here, and can make the scale something like 1. And now if we play, now you will find the far smoke is more natural and less sticky to the curve. We can also make the swirl size 0.1, make the scale something like 3. We can also here in the buoyancy, we can increase our buoyancy to 10. And you'll see more natural effect here. Maybe we can just here, let's make the swirl size something like 3. Scale, let's make it 10. I just want to show you guys. I think 10 is too much. We can something like 6, for example. Still too much. We can use stick to 3 again. And here is the far smoke. It's going to float away. As you can see, it's not going to really match the curve, which is really great. If you see here in this area, it's floating away. I just wanted to show you guys, but the scale surely is too much. So I'm going to stick to 1. And what we can do now, if we, for example here, set this to 0.5 and play my simulation again, you will see that it will stick more to the curve. Okay, because this means when the distance is, if the distance is 1 or more, it's going to put 0.5 here in the mix, so it's going to be between the input 1 and the input 2. Okay, it's not going to be purely our smoke velocity, so this is going to make it stick more to the curve. If we set it, for example, to 0.1, it's going to stick much more to the curve. So what we can do, and make this one again, what we can do, we can just promote this parameter, and we want our user to control the curve thickness, curve thickness. But the problem now, if the user sets the curve thickness to 1, we will have here 1, okay, and this will make it float more, or it will make it this will make it less sticky, okay. And to avoid this, we can create a complement node. So now when the curve's thickness is set by the user to 1, the complement of 1, 1 minus 1 is 0. Sorry. So when the user sets the curve's thickness to 0, okay, it's going to the complement of 0, 1 minus 0 is 1, and here this is going to input a value of 1. So now the user is going to control the curve's thickness, and we can set the default value 0.1. So 1 minus 0.1 is 0.9. So now we are going to have this number here, 0.9. Okay, and I don't know why it's just like this here. Let me yeah, I think it's working now. So now we have a parameter to control the curve's thickness, and we have something like this now. Let me flip book it and show you guys, but before this we want to show our simulation better. So I'm going to create a geometry node and import my simulation here. So I'm going to add the DOP import fields. The DOP network is going to be this DOP network. Our object is going to be our smoke object. I'm going to take this appress smoke and add a volume visualization node. Okay, we can put the maximum resolution and the density scale to 10. Okay, and let me add some lights. I'm going to hide this now. You'll add lights like we did before, and add a spotlight here. For example, we can make the exposure larger, something maybe like this. We can make it yellowish. We can add another one here. Can make it more blue. And maybe in the import here, we can set the shadow scale to 1.2. Okay. Maybe we can add another light from behind here. Can add a spotlight here again with less exposure, something like this. And we can create a camera. Okay, we can also go to our DOP network and increase the resolution, something like this, and then the gas turbulence. Okay, I think it's enough for now. Now let me flip book the simulation and show you guys. So now guys, here is our simulation, and as you can see, the smoke that is far is going to create interesting shapes, and this is really great. Now the last thing guys I want to show you, you can just create an OTL here and call it curve force, and I will show you guys my OTL, but you'll just edit the parameter interface and go to the sub guide. You can grab whatever you want from here, and then here in the gas field bob you can grab whatever you want from here and create your OTL. I will leave this for you guys, but also sorry, don't forget to add the show guide geometry here, which will show your curve, and don't don't forget to put the display flag here in the volume trail. So if you now play, my viewport is very buggy, so now it's going to show you your guide geometry, and here we go. So now I will show you my version, because if I create it now for you, it's going to be very boring, and we did this a lot before, just grabbing the parameters, putting them. So this is my version. Here we had this geometry source, which is the object merge object here, okay? Because we can select any curve that we create from this, and we have the maximum radius, the curve's thickness here in this tab, curve force, and we created these parameters, and we also may put here the maximum distance of velocity blend, and here we have the tabs for every force, for the flow force, follow force, the orbit force, the suction force, and inside every tab we have the scale of this and the ramp, the distance between it and the curve between, and we have the ramp here, the follow force from curve ramp that we created, and the same for the orbit and the suction. And here we have the global force, where we have two ramps that we created, the from curve ramp and a long length ramp. And as I told you, we can create also a long length ramp for all of these forces. And we also had this shaping here. If you remember, we created here this ramp here, a long length radius ramp, and also we have the resample here. We can take this resample length. So this is what I did here, the resample length and the radius along the curve, sorry, the radius along the length here. And we had our geometry here, the show guide geometry, and the trail length is just this length here in the volume trail, which can increase or decrease your trail length here in the viewport. And this is it. You can just start putting the parameters like this. This curve force is just a folder with the forces inside it, and we have another folder here for the guide. I encourage you guys to create your own version, because I don't want to lengthen the videos with something that we already created before. So this is how you can create a curve force. Of course, you can use this in any particle simulation too, but you will just use a node called pop advect by volume, and we will talk about particle simulations. So now let's apply the curve force here in a pop network. Okay, so this is just a pop network. You can just create it from here, source from object, source particle emission, and you can create it yourself by creating a pop object, a pop solver, and this pop source you can just connect it here to the sourcing, and this pop source in this pop source you select a geometry. So choose I chose my sphere here. Okay, and you can emit from the sphere. So I just chose my sphere, and I here in the attributes set the initial velocity. I gave it a value of 111. So this is what we have now. We have particles going in every direction here, and I want to apply my curve force here to the particles. So we can do this by putting a merge node here. Okay, let me hide the guide geometry. Okay, then this is my curve force, and if we play, nothing will happen, because if you go to the spreadsheet here, you will find that the pop solver doesn't deal with fields. It does not create the velocity field, the density, and all of this stuff. It works with the particles as points only, and it does not work with fields. Smoke solvers and pyro worked with fields. Flip solver worked with fields and points, but the particles are just points. We don't have fields. So we are going to add this curve force here to make it suitable for particle simulations. We are not going to edit the sub guide here, because the sub guide here creates our force, and we are just going to edit this gas field VOP. We will no longer use this gas field VOP because it works with fields. We are just going to use a pop VOP here, and in this pop VOP we will just do the same here in the inputs. I can copy this and copy this one too. And now here we can copy all of the nodes from this gas field VOP. We can here in this pop VOP, we can paste all of these nodes like this. So let me now connect the position here to the position of the particles in this volume sample V, and the file is here. We're doing the same thing, but instead of the position of the voxels, we are now accessing the position of the particles. It's the same thing if you think about it. And the PC open, we're going to connect it here and here. So now we here in this pop VOP, we don't deal with fields. So now this bind here vel is not going to do anything. It's just going to search for an attribute on these points called vel, and is not going to deal with the fields. In the gas field VOP, when we binded a field here with the bind node, or when we just created a bind node, we just if we just set the name to velocity, it's going to grab a field. But here the bind node grabs attributes from the points, so we already have the velocity here as v, not vel. So either you rename this vel as v, or you can use the velocity here of the particles instead. So connect it here and connect it here, and finally here also we can now delete this vel and delete this vel. We can export this as our particles velocity. So if we now connect this pop-up instead and set the curve's thickness, yeah, we can set it something like 0.5, 0.5 like this. If we now play our simulation, it's not working. Why it's not working? Let me see. We are doing everything as it should be. Position and velocity. No, I changed the curve's thickness in the gas field valve instead of the pop valve. I'm sorry. And here we go. We should have everything working now, but it's not working. So I realized my mistake here. I chose the passes here wrongly. This is the DOP network 2, and this node is curve force 1 subguide, and here out velocity, and then out curve. Okay, now if we play, we should have it working, and yeah, it's working now. So this is how you can apply a curve force for the particles with the same controls. So what we did here is just we did the same process, but instead of velocity field, we connected this velocity, and now everything is working fine. So thank you guys for watching. This was the example of creating curve forces in Houdini. And of course you can use either the pop version or the field version to manipulate fluid simulations. As we said, fluid simulations work with both the fields and the points. Okay, thank you.